So instead of using the right endpoint, why not the left endpoint? We're doing an approximation. We're choosing how to make these rectangles. We're trying to explore the different ways we could do this. So now we still have the same delta x of 1/2 in each case. Now the question is, what would happen if we used the left endpoint of, say, this first interval, use the value of the function there to make the rectangle? So now we get a bigger rectangle, all right? And then we use the left endpoint of the second interval, point up here, and then we use that, and so on, and so on. Okay, so let's do the calculation all over again. So this time we're going to use x0, x1, x2, and x3 because we're using the left endpoint each time. Those are the 4 values that we're going to calculate at. So the area is approximately f of x0 delta x, the height of the first rectangle, times the width of the first rectangle. And same for the others. Very like we did before, we factor out a delta x. And now we get these function values. So the only difference is the first one we're using is x0, which is 0, and then 1/2, then 1, then 3/2. And we still have our delta x of 1/2. So now, just bringing that 1/2, still there. We know the function, so we can go ahead and find these values. Well, that would be 5, and then we calculated the other ones before. This was 19/4, this was 4, and this was 11/4, which would give us 33/4, which is 8.25 square units. Okay, so now because the function was decreasing, this time because it was decreasing, when we used the left endpoint, we got an overshoot of the region we wanted. So we got more because we got included this area here that wasn't there. So for a decreasing function, the left endpoint approximation gives us the upper sum for this many intervals. That's actually pretty informative because right now we know we have a lower sum that we found before, the 6.25, and we found an upper sum of 8.25. And so even though we don't know the true area, we actually do know it's between these two values. So we've garnered a decent amount of information there. Now, if you're asking, could we have used some other point? Oh yeah, it might have made sense to use something in between. So the midpoint approximation. So if we ran through this again, I'm not going to go through the details very closely, but if instead we use the midpoint of every interval instead of a left or right endpoint, it would work out in a similar manner. And again, the only difference we would see is we would see the different points that we're evaluating the function to get the heights. And if you went ahead and did this, you would get 7.375 square units here. Okay, so another approximation. So that brings us to a good question. These are all approximations. How do we determine the exact area of such a region? All right, so we broke it up into 2 intervals initially, then 4 intervals, and we looked at the 4 intervals in 3 different ways. Well, here's the thing. We need to look at how many rectangles? Well, infinitely many rectangles. Okay, so that's the idea. If we want the exact area, we know that more rectangles is going to give us a better approximation. Exact, that's going to come from infinitely many rectangles. So I'm thinking this will be about limits. Now, in order to do that, we're going to need some tools. And one of the first tools is we're going to need a way of adding up a lot of rectangles on our way to adding up infinitely many areas of rectangles. And that means to add up a lot of things, we have something called sigma notation.